Okay, today we're going to go over the second fundamental theorem of calculus. Now, sometimes this theorem will be referred to as the fundamental theorem of calculus. It doesn't really matter. It's the same idea. It's simply a way to derive an integral. Sorry, yeah, derive an integral where one bound is a function and the other is a constant. And I'll show you what I mean by that. So let's say we have the function f of t, and we're taking the integral from a to x of f of t. Now, if we were to take the derivative of that, you'd end up with f of x, and I'll show you how. So if you recall from the first derivative test, well, first let me start off by saying that let's let capital F of t be the antiderivative of the lowercase f of t. Meaning if we were to take the derivative of capital F of t, we'd end up with the function of the lower f of t. So now that we've got that cleared up, by the first fundamental theorem of calculus, this right here, this integral, is actually equal to capital F of x minus capital F of a. And if you don't understand this, then I'll link my my video on the first fundamental theorem of calculus in the comment section, or sorry, the description. So this over here is practically equal to, and I'll rewrite this, the derivative of f of x, capital F of x, minus capital F of a. And so you're probably wondering, how is this equal to f of x? Well, this over here, capital F of a, is a constant because we're replacing all instances of an independent variable with just a constant. And so this ends up being equal to 0 when we derive it, because the derivative of a constant is 0. And so all we're left deriving is capital F of x. Now, if you look over here, we can see that capital F of x, when taking the derivative of, is equal to lowercase f of t, or lowercase f of x. And so when because this is the antiderivative of f of t. And so we really end up with f of x equals f of x. So what you're doing is you're replacing every instance of your normal equation. You're replacing every instance of t in your integrand with x. Now this over here is a more specialized, it's a more generalized form. It says that the derivative of the integral from a to g of x, f of t, is equal to f of g of x times g prime of x. And this seems a bit more confusing, but it's really just the same thing over here. Except I put this, I feature this other equation as well. Even though it's more specialized, it's much more common. But nonetheless, what you're doing here is you're going through the same process. You're replacing every instance of t with g of x. Same as over here, where you're replacing every instance of t with x, except you're also taking the derivative of g of x. Now, g of x is just it's used to express any function. It could be x squared, it could be e to the power of x, it could be x. So, for instance, if we replace g of x with x, then we'll have to replace this with x as well, and we'd have to replace g prime of x with the derivative of x, which happens to be 1. And you'll notice that this ends up being f of x, and that's why these two are the exact same, practically, when g of x is equal to x. But yeah, it's just a more generalized form. That's it. That's the entire second derivative test. Okay, for some reason I said that was the second derivative test. I meant the second fundamental theorem of calculus. Anyways, this is practice problem 1, the first out of 3. It's quite basic. We're told to find the derivative of the integral from 3 to x of x squared dx. Now, the common expression, or let's equate this to the general equation for the fundamental theorem of calculus, or at least the answer, that being f of g of x times g prime of x. Now, since the upper bound happens to be x, we could also just say that this is equal to f of x, which it is, but I prefer to use the more generalized term. Anyways, we can replace, we can substitute g of x in with x, and so this is actually equal to f of x times the derivative of x, which is 1. So now all we have to do here is we have to replace or we have to substitute or t squared in with f of x. So this entire function is equal to t squared. Or this entire derivative is equal to t squared. And as proof, we're going to go through it again, except we're going to first find the actual derivative and then we're going to derive it. We're not going to use the second fundamental theorem of calculus, which is essentially like a shortcut. So let's begin. This over here, if we take the antiderivative of t squared, we're going to end up with 1/3 t cubed. Normally we'd add a plus c, however, since we're dealing with bounds, it's not necessary. And we can employ the first derivative test, and we can see that this is equal to 1/3 x cubed minus 1/3 3 cubed. And there's no need to simplify because I'm now going to take the derivative. We found that the integral from 3 to x t squared dt is equal to 1/3 x cubed minus 1/3 3 cubed. So this over here is equal to this over here. So from here, we're going to find the derivative with respect to x of 1/3 x cubed minus 1/3 3 cubed. And since the derivative of a constant is 0, we can just cross out this area here. We can say minus 0 if you wish. Now we have to find the derivative of this term over here, 1/3 x cubed. Using the power rule, I've also made a video on that. Using the power rule, we can see that this is actually equal to x squared. And I just realized that this over here should not be t squared, it should be x squared. I don't know why I said t squared. We should have substituted the integrand. We should have substituted the t in the integrand with x. And so it should have been x squared. But as you can see, even despite my mistakes, they are equal. So this integral is a bit more difficult to solve, and this is why the second fundamental theorem of calculus is important to memorize, because this over here would be quite difficult to integrate normally, and so we're going to use this shortcut instead. But first, let's try to fix this up a bit. This is actually equal to the negative derivative of the integral from 3 to x cubic root of t squared plus 1 dt. I forgot that, and I may have forgotten that in previous examples as well. I don't know. But the reason why this is actually the negative version of this over here is because we're reversing the bounds. And if you reverse the bounds of an integral, you are negating it, I suppose. But yes, that's what we have so far. We might as well just take this negative out. So all we have to solve here is the derivative of the integral from 3 to x cubic root of t squared plus 1. Now, using the formula, or the answer to the formula we've previously memorized, the one for the second fundamental theorem of calculus, we know that this over here is equal to the negative, because of this negative sign over here, negative cubic root of t squared plus 1. Sorry, God, I keep forgetting that I'm supposed to be substituting x squared in for t. So it's actually x squared plus 1. And there's no need for a c. And one reason why it's best to write an antiderivative using the second fundamental theorem of calculus is because you don't have to add the plus c on at the end. But that may be a bit advanced for you. If you didn't understand that, don't worry about it. But this is the answer to the derivative of the integral above. It's really that simple. You just have to substitute x in for t. Okay, so typically people assume that the answer to the second derivative test is f of x. Now, that is generally true, of course, but when you dive into functions that aren't as simple as just x and some that are quadratic and whatnot, the solution gets a bit more difficult. So it's best to express the answer to a second fundamental theorem of calculus as f of g of x times g prime of x. And as I said, these are the exact same things. It's just better for this equation to use this general term. So we're told to find the derivative of the integral from 3 to x squared of the square root of t squared plus 1 dt. I guess I forgot that again. So first, we might as well simplify this a bit. F of g of x is f of x squared. That is because we're going to assign x squared to g of x, because that's the only function in the bounds, times g prime of x. Now the derivative of x squared is 2x. So this is what we have so far. Now we just have to find f of x squared. And that means this over here, this integrand, is actually equal to f of t. And so we're going to substitute every instance of t with x squared. And so this derivative of the integral is equal to the square root of x to the power 4 plus 1 times 2x. And that's because I substitute t in. Let me write this integrand over here. In place of 2, I put x squared. And since t is squared, we have to, of course, square x squared as well, plus 1. And of course, that's x to the power of 4 plus 1. And so that is our answer for the final practice problem. If you have any suggestions for future videos, please put them in the comments below. Thank you.